Scott Guzewich is a scientist in the Planetary Environments Laboratory at NASA's Goddard Space Flight Center down in Greenbelt, Maryland. And he picked up a PhD in Earth and Planetary Science from Johns Hopkins University in 2013. His research interests include terrestrial planet atmospheric dynamics, aerosols, and chemistry, and conducts research through spaceflight mission data analysis and general circulation modeling. And he's currently a member of the Mars Science Laboratory and Mars 2020 Rover science teams. It's a pleasure to have him here for the first time. Please welcome Scott Guzewich. Hi, Scott.
Hey, how are you? Thanks for having me.
Thank you. Thanks for coming.
Yeah, so let me share my screen. And we'll put this into presenter mode. Yeah, so thanks for having me. Look forward to a good discussion, and I do hope it is a discussion. As I mentioned to some of you at the beginning, I don't like just kind of speaking to silence for for a while. So if there are questions, I hope they get asked, and we can make it a fun interaction. Because I think that's the best way to do these sort of virtual events when there's not face-to-face contact. So I'll talk about here roving Mars with Curiosity and Perseverance. And of course, I think I just have to lead off here with the exciting event of the year, which was Perseverance's landing on Mars back in February. A really spectacular moment, especially kind of coming off of the final integration and testing of the spacecraft was done, obviously, during COVID. The launch was last July in the middle of COVID, and which unfortunately meant I missed the launch. Had to watch it on TV just like the rest of you. But it really went off without a hitch, just picture perfect. And for the first time ever, we got high definition views of the landing while it was in process from the lander itself. So there's a few different, there's a whole series of cameras. Actually, I can't remember the exact count, but I think it's close to a dozen cameras sort of pointed off in each different direction during landing. And so you're seeing here these animations of some of the different viewpoints. So we had cameras on the rocket descent stage. That's in the upper left animation there. You can see that rocket descent stage. And that's called the sky crane. And so we had cameras on that pointed downward at the rover. That's the still image on the lower right. This beautiful shot of the rover descending on the 3 cables with its wheels deployed. And you can see the dust being kind of kicked up by the rocket blast on the surface. We had cameras on the top of that descent stage, the sky crane, looking up at the parachute deployment. This is a really important moment for understanding how the physics of parachutes work. It's kind of this funny thing that parachutes are something that you can't really model. You have to actually test them. The European rover right now, the ExoMars rover, is having a real heck of a time with their parachute testing. They've failed a few times. They couldn't get it to work. And they've actually involved the Jet Propulsion Laboratory engineers because they're the only ones who seem to know how to do this to kind of work their parachutes, because it's really hard to do. And so kind of having this camera image of a parachute actually deploying in the Martian atmosphere is really, really valuable to sort of make this happen in the future, hopefully far more often. So you see that happening up there in the upper right. And then, of course, we had cameras on the rover itself looking up back at that sky crane rocket stage as it's lowering down. And then you see at the very end of the animation flying away. So it flew away, crash landed. We actually have this picture. I didn't include it in the presentation. We have a picture of this essentially, plume of dust and smoke that it kicked up as it crash landed a few kilometers away from our rover. So really amazing. You can there's a whole series of these videos on YouTube if you want to search through them, because they're really fun to watch. There's so much detail in them, and the resolution is better than the animation I have here. And this landing was not it was not easy. So Jezreel Crater, where we landed Perseverance, is the most complicated and sort of dangerous terrain that we've ever landed a Mars spacecraft on before. If you kind of look back through history and compare, the size of our landing zones have gone from, Viking scale, which is, I'm trying to think of how big those landing ellipses were. I think they're kind of on the order of hundreds of kilometers long. So you're talking something like the length of Connecticut type. We want to land Viking in Connecticut was kind of like the scale that we're talking about here. And they've kind of progressively gotten smaller and smaller and smaller as we've gotten better at this. And they've also, as you can see here at Perseverance, they've gotten rounder. So instead of just kind of being really long and skinny, which is how kind of the earlier ellipses are, now they've kind of gotten rounder. And the reason is that Perseverance was actually able to sort of fly itself as it descended through the atmosphere. So it entered the atmosphere, and as soon as the heat shield popped off, it had a camera on there that had a very precise kind of map of Jezreel Crater. Got some feedback. So it knew precisely where it was in relation to this landing zone. And it knew precisely where it was relative to all the danger spots. So that really kind of weird looking psychedelic image on the right is what the computer saw. So it saw, okay, all these red and yellow places, those are bad. I can't land there. That's dangerous. I need to find a blue spot. And so it navigated itself to that tiny little green dot right there in the middle of all that red. This was not easy. This was really complicated, and it did it extremely well. And so it found this perfect little, very small scale safe spot that it put itself down on. And I think it hit the target by under 2 meters. So about the length of a person's height. That's kind of about how close it got to where it was aiming for. So really, really precise. And this is really important for human landing missions, right? I mean, we're going to send sort of supplies in advance of astronauts, right? And we can't have your food and your fuel 20 kilometers away from where you put down. That puts a lot of burden and stress on the astronauts. We need those things to be right next to each other. And now I think we've kind of demonstrated some of that technology that we need. What Perseverance also was carrying was the first helicopter to ever go to Mars. And it's called Ingenuity. And this was a tech demonstration. And you can see there a picture there as it was doing testing out at the Jet Propulsion Laboratory in California. This is a really interesting little piece of equipment. So Mars's atmosphere is extremely thin. It's very low density. And if you know anything about helicopters, you're sort of generating lift by spinning those rotorcrafts and kind of providing some kind of downward pressure on the air around you. But there's no stuff there to put that downward pressure on. You can't really generate that sort of lift. And so the way you get around that on Mars is that you have these rotors going extremely, extremely fast. And I think it's something on the order of 5 times or so what an Earth helicopter rotations are in terms of speed. So it's rotating really, really fast. And then of course, the whole unit itself has to be very light because you just have to generate as much lift as you can with those 2 rotors. And those 2 rotors are actually quite long. They're several feet long. So you're really trying to generate as much lift as you can. So this whole thing only weighs a couple pounds. And they put a little camera on it, and it's trying to just demonstrate the physics of this in the Martian atmosphere. And lo and behold, it worked. So this is actually a little animation there. You can see the shadow of the helicopter as it's flying across there and kind of snapping pictures as it goes, looking downward at the surface. And so it did a series of flights, and those tracks there are in green on the map on the lower left, where it just sort of first it kind of went straight up and hovered and went back down. It did that a little bit more, went back down, then it kind of did side to side and went back down, and then it actually started kind of going somewhere else and landing there and staying there. And now it's sort of hopped along to these different spots out ahead of the rover's path. So it's sort of been going from this operational or from this tech demonstration to a sort of operational scout, where it's sort of looking ahead and saying, hey, here's some interesting stuff over here, come look over here. This is a good place to drive, this is a bad place to drive, that sort of thing. And so it gives the rover team a little bit of sort of advanced look as to where it can go. And that's, pretty helpful. We have really good images, of the terrain, but, there's always stuff that sort of surprises you when you're kind of on that face-to-face scale versus when you're way up in orbit looking down.
How is the helicopter doing now? Is it still functional?
It is. So we just had what we call conjunction. And I don't know how familiar everyone is with that, but basically Mars was on the opposite side of the sun from Earth over the last few weeks. And we just came back out of conjunction this past weekend, where there's enough angle between the Earth, Sun, Mars line that we can get some communication back to Mars. So for the last 3 weeks, both rovers and Ingenuity were basically just sort of parked in one spot, doing very minimal work. and Ingenuity was not doing much. It had a little bit of a issue right before conjunction, and they're sort of testing that right now. I mean, it's lived well past its design lifetime. It was only designed to do a couple flights, so it's already up to 13, and I believe the engineers are pretty confident they can get it to go again. So we're well past sort of the design lifetime for Ingenuity.
Scott,
But,
I was wondering too, with as Mars goes in and out between summer and winter, the percentage of the atmosphere changes. Does that make it harder to fly Ingenuity when we have thinner atmosphere?
Yeah, that's a really good point. Yes, it does. So that's actually something that's kind of coming up, where we're having that concern where the atmosphere is getting thinner right now. So a lot of Mars's atmosphere actually physically condenses onto the polar caps in wintertime. And so we're kind of at this stage of the year where there's a healthy amount of the atmosphere condensed onto the polar caps. And so the air is just physically less dense. So they're having to increase the RPM for Ingenuity to get it to fly with that same height. Yeah.
How much does the atmosphere's density change in the course of a season? That's remarkable. I don't even know. Does the Earth's atmosphere likewise change in density to that degree?
Well, it's the carbon dioxide. It's the poles that are sucking all the carbon dioxide out. I think. I mean, Scott's the pro on this.
Yeah, that's exactly right. So our atmosphere does not do that, right? Our atmosphere, nitrogen and oxygen, we come nowhere near the condensation temperatures of either gas species. You can actually get kind of close to the CO2 condensation point in like the coldest days of Antarctica, but we don't get there. On Mars, though, that's certainly not the case. We have the atmosphere is 95% carbon dioxide, and it certainly gets cold enough at the winter poles to condense carbon dioxide. And so you have a pretty massive percentage of the atmosphere, 25-30% of the atmosphere that condenses in and out of the polar caps on a seasonal basis.
And one more question about Ingenuity. Can you use it to fly and to blow dust off the panels on Perseverance? Would it work like that?
That's a good question. So Perseverance is nuclear powered. Both rovers are nuclear powered, so we don't have that concern.
Wow.
For solar powered diminution, like the InSight lander, which is solar powered and it's stationary lander, is having some real challenges right now because it has not gotten the sort of wind cleaning events that the Opportunity and Spirit rovers did, that kept them going for a long time. For whatever reason, where InSight is, that doesn't seem to happen very much, and the dust has just kind of continued to thicken and thicken. And so most likely InSight will just shut down at some point, in the next 12 months or so. But to your point more directly, we have video from the rover looking at Ingenuity flying, and you can see dust being kicked up on the surface by the motion of the rotors. So, the physics seems to work where you could do that, where you could, just blow some of the dust off. What makes it a little tricky is Mars dust is very clingy. It's very electrostatically charged. And so you can't just sort of like as easily sort of, blow it off or shake it off like you would on Earth. It's more like, a real staticky dust bunny than just, the dust on your computer screen.
Interesting. Thank you, Scott.
Yep. So, why do we go to Mars? And the reason I think that I try to tell people is because Mars was very much like Earth, we believe, back, 3.5 to 4 billion years ago. Both planets were very young, and we think both planets had all the conditions that allowed life to begin on Earth around that time. And so we, of course, want to know if that happened on Mars. When Curiosity first arrived back on Mars in 2013, or 2012 and 2013, very soon after, it found this rock here in the upper left, this conglomerate rock. And you see all these rounded pebbles kind of coming out of this combination rock that's kind of been stuck together. And it's just a dead ringer for these sort of things you see on any sort of riverbed or lake bottom on Earth. And we had suspected that the bottom of Gale Crater was an ancient lake. And sure enough, we see these rocks that are just absolutely typical for places where you have liquid water on Earth, that round pebbles through that just sort of knocking action over time, water flowing and bumping things together. And then over time, they sort of stick together with little bits of sand and dust and dirt and things like that. And both rovers have, these long robot arms that drill into the surface and can sample the material in them. And so, both rovers we've sent to places where we think liquid water existed in the past, perhaps in different sort of formats and in different sort of periods of Mars history. Gale Crater seems to kind of tell us a story about the drying out of Mars over time, where there were probably periods where it had, standing lake with a river flowing into the crater, and other times it probably was more sort of groundwater kind of feeding up to the surface in rare times. And the whole planet sort of drying out. And so it sort of tells us the history of the planet through the story of the geology. And of course, the real question we wanted to answer is, could Mars have supported life? And so we're going to these places where we believe the geology would support the collection of those materials that tell us that answer. So you can see this is a picture of Gale Crater on the left in the color, and you see these really finely layered, thin rocks. And those are probably sedimentary rocks that were laid down in liquid water, where you have just sort of slow deposition, sediment settling out of water over time and creating those really kind of thin layers and stacking them one on top of each other. And then, Jezreel Crater is just an absolutely perfect representation of a river delta. So you can see here, can you all see my cursor on the screen? I think.
Yes. Yeah. We can see it.
So you can see the river here flowing in. This is the crater rim along the edge here. The river flowed into the crater, and it then, when it got to a slower, stagnant body of water, just like the Mississippi does in the Gulf of Mexico, it begins to branch out and kind of deposit this load of sediment onto the surface. And so you have, of course, the classic Mississippi Delta with all these branching channels. If it wasn't, kind of kept open by by commercial reasons, probably be even more branching channels and changing river flow patterns. And on Mars and Jezreel and in other craters as well, you have really the exact same pattern. You can see these curving branching channels and this thick, erosion-resistant layer of material, which is believed to be the sediment that was sort of collected over this whole rivershed, this watershed, and then brought back into the Jezreel Lake, where it just kind of built up over time. And so the rover now is kind of off screen relative to this viewing angle, but it's going to be driving up this delta remnant and sampling along the way, and then eventually kind of drive probably either up the river channel or kind of adjacent to the river channel out into the watershed around it. So then, of course, what we really want to know is, if Mars was so similar to Earth 3.5 to 4 billion years ago, and they both had some sort of thick atmosphere, and they both had liquid water on the surface, and we were quite confident they both had the chemistry to support the formation of life, the elements like carbon and nitrogen and phosphorus and things like that, then what happened to them? And of course, the simple answer is, well, Mars is small, and so it dried out and got cold, and that is kind of the 0th order answer, but it's a lot more complicated than that. Mars probably had a magnetic field long ago. We know from InSight, we know some measurements of Mars's core today. So it probably had a magnetic field. It probably had a thicker atmosphere, but Mars could not sort of retain that magnetic field. It could not retain that warm kind of active geology. And so there was no kind of replenishment of the atmosphere, not on a consistent basis, at least. And the active early sun just sort of constantly stripped away material out into space. And that's still happening today, 4.5 billion years later. So we have a mission around Mars called MAVEN, which is specifically looking at this process. We call it atmospheric escape. And you can see here this thin but bright area showing the loss of carbon to space. That's carbon dioxide going up into the upper atmosphere. The high energy particles from the sun sort of split it apart. And so you kind of split out the carbon, you split out the oxygen, and you lose it out to space. And then, of course, specifically for water, we want to know about hydrogen. And so you see this huge kind of extended hydrogen corona around Mars as the limited amount of water that is in the atmosphere is also split off in oxygen and hydrogen. And the hydrogen, especially because it's so light, is often lost to space. And so
Scott,
this isn't a lot.
Oh,
Yep.
we had a question come in too, just was kind of on the topic of this too. Why are there more meteor craters on Mars than you see on Earth? Now, obviously, Mars has a very thin atmosphere, and Earth has a thick atmosphere. But why are there more meteor craters? And this is from Morris that had asked that question today.
Yeah, good question. And it is really just because of the thin atmosphere. So Earth is obviously bigger. So we're a bigger target just by size, and we're a bigger target with more gravity. So we actually sort of pull in more debris, right? There's maybe a little bit of a counteracting balance because Mars is a little bit closer to the asteroid belt, but Mars is smaller, it has less gravity. But because the atmosphere is so much thinner, a lot smaller objects can reach down to the surface. And the rovers actually, both rovers have seen iron meteorites just lying there on the surface. And going back to Spirit and Opportunity, they saw several of them. And they're all, kind of like football sized or maybe beach ball sized iron meteorites that have survived down to the surface. Some have even made a tiny little crater of their own. Others just seem to sort of have like soft landed or, nearly soft landed on the surface and just are there now for the rest of time. And so, on Earth, of course, we get iron meteorites that can kind of survive down to the surface, but a lot more is ablated, a lot more is burnt up in the atmosphere. I mean, our atmosphere is, several hundred times thicker than Mars's. So we can be shielded from a lot of those smaller objects, whereas Mars is not, and it's just constantly peppered with meteorites of all sizes.
And obviously on Earth too, we have erosion. So you don't see, we still have some craters that you can see on Earth, like in Winslow, Arizona. You can see there are craters here, but on Mars there is no erosion, or at least hasn't been in billions of years, right?
Yeah, well, there's no water erosion, right? There is some erosion by wind, but it's a much slower and more gradual process. And so the wind erosion is just much less efficient because there's just much less material that can actually erode it away. Water erosion is, as you mentioned, so much more efficient and erases some of those craters. But again, the minimum size of an object that can reach the surface of Mars is a lot smaller. And so we actually have had spacecraft in orbit now for several decades, and we've watched new craters forming, and these are often quite small, and we can watch them kind of get covered up by dust over time. But some of these fresh craters are only a few meters wide, where on Earth, we really don't get objects that size that can crater onto the surface.
I had another question too from Steve Schreier that just throw in here too, as long as we have a pause. Can Perseverance detect methane emissions?
Perseverance, no, but Curiosity, yes. So Curiosity has an instrument called SAM, the Sample Analysis at Mars, which is actually built and operated by the group that I work in at Goddard Spaceflight Center. And it is a mass spectrometer. And so it's designed to measure the chemical composition of rock materials that we drill and drop off into the laboratory, into the mass spectrometer on the rover. It's inside the rover. And it also has a little valve we can open up and we can suck in a little bit of atmosphere and measure the gases in the atmosphere. So Curiosity and the SAM instrument have measured methane in the atmosphere and measured how it's changed over the course of the mission. Yes.
Great. Thank you, Scott.
So I've talked a lot about geology because that really is the primary mission for all the rovers that have been sent to Mars. But that's not what I do really on a regular basis. I'm an atmospheric scientist, and so my role in the missions is to study the climate of the planet, study the atmosphere of the planet, and that's sort of most exemplified by the massive dust storms that Mars has. This is a really unique feature of the Martian atmosphere. And it's one that I find really fascinating. And so about 3 years ago, in summer of 2018, we had our last global dust storm on Mars. So periodically, on a frequency that seems to be about every 2 to 5 Martian years, but we don't quite know, we can't predict them. We get these global dust storms where dust completely shrouds the planet and you really can't even see any surface features from orbit. And this animation on the left is showing the growth of the storm, kind of highlighted in the orange region. And you see the Opportunity rover, which unfortunately the storm actually caused its shutdown, and then the Curiosity rover over on the other side of the planet. And you can see that the storm started near Opportunity, and that was actually kind of the reason that it failed, was because it was just in this really thick cloud of dust for a very long time, and its batteries could not maintain a charge because there was no solar power reaching the surface. Curiosity, though, is nuclear powered, and we were perfectly fine operating throughout the storm. And so that animation on the lower right is our view of the crater rim, which is anywhere from about 25 to 30 kilometers distant from where we were at this time. And you can see the view of it get foggier and foggier and then completely gone. And you can obviously see the color change as well. And visibility got down to about 2 to 5 kilometers during the storm, which is about typical for like a rainy day or maybe a light snowy day on Earth. Quite low for Martian standards, where sometimes you can see 50 to 70 kilometers depending on the terrain features. So it was really incredible to watch from the surface. This is the first time we had meteorological sensors inside such a storm since the Viking landers back in the 70s. So this was a really great opportunity for science. And looking down at the ground, we see all these features kind of in person versus from orbit, and that's what's really fun. So right after landing, this top animation is from Jezreel Crater from Perseverance, and it's showing this really strong gust of wind come by and lift dust off the surface. And this might not look like much to the random person who maybe sees this all the time, like on a windy day in the desert, right, here on Earth. But this is not something we've seen actually from the surface of Mars really at all before, where we just see kind of what we call straight line winds, kind of blowing across the surface and lifting dust straight into the atmosphere. So that was really, really exciting to see. And then on the bottom is the ubiquitous Martian dust devils. This is in Gale Crater, looking up towards Mount Sharp there in the background. And you see the beautiful column of dust being lifted off on the ground. And again, we see these all over Jezreel Crater. We actually saw a dust devil in Jezreel Crater while the rover was landing. If you look at the animation of the ground from the rover's descent camera, you can see a dust devil kind of blowing along the crater rim as the rover's landing. They seem to be all over the place in Jezreel. And they're quite common in Gale Crater as well. And these tell us a lot because they're kind of present all over Mars, and they supply about half the dust of the atmosphere. So Mars's atmosphere always has some amount of dust in it. There's more in certain seasons than other seasons. But it seems like these sort of dust devils, which just kind of blow around the planet all over the place, eventually kind of supplied a lot of that background dust haze into the atmosphere. And Mars's atmosphere does have water vapor, and it does have water ice, and so it produces these beautiful cirrus clouds. This is in Gale Crater, kind of looking up in evening and twilight, and the light is illuminating these very high altitude water ice clouds that look, for all the world like any sort of cirrus cloud does on Earth, on a sunny winter day. You can see all that very fine texture, all that structure, which again is very reminiscent of clouds here on Earth. So we have these sequence of images that we take with both rovers looking up to study water cloud. And this is actually the time of year right now on Mars where we get sort of the most water ice clouds. There's sort of a cloudy time of year and a not so cloudy time of year. And right now we're in that cloudy time of year. So we're doing this quite often. So what Perseverance is there to do, of course, is to be the first step in a really ambitious, sort of crazily ambitious sample return effort. So if you probably know, we have samples from the moon. We had samples from the moon, both from our robotic landers, and we had them from, of course, the Apollo astronauts, right? The Apollo astronauts brought back tens of kilograms of material back to Earth. The Soviet landers brought back some material from the moon. We've brought back, tiny amounts of materials from other objects in the solar system. We've brought back a little bits from comets. The Japanese have brought back some from asteroids, and we have a mission called OSIRIS-REx, which is bringing back a sample of an asteroid right now. But really for decades, we've wanted to bring back a sample from Mars. And of course, because Mars is such a big planet and it's so far away, this is a really, really challenging activity. And sort of the plan for this has been debated over a really long time. And, it's been decided ultimately that it makes so much more sense to send a rover like Perseverance, where you can get all of the geological context, you sort of know what you're getting before you bring it back to Earth. There were some earlier ideas where you would just land a lander sort of like Viking anywhere on the planet, have it grab whatever rock it can reach nearby, throw that in a rocket and send it back to Earth. And there is some value to that, but given the price tag for this sort of mission, it seems to be so much more valuable if we can tell the history of Mars in these samples. And that's really what Perseverance is hopefully going to do. It's going to give us the book of Martian history in a few dozen rock samples that it's going to bring back to Earth, hopefully in about 10 years' time. So Perseverance is collecting these rock samples in these series of small tubes. It's going to leave them on the surface, or perhaps, depending on its longevity and its livelihood, it might bring them to this rocket that we're going to launch and land on the surface in a few years' time. They might also have a small fetch rover that'll come and kind of collect all of these and bring them back to the rocket. Oops, wrong way. And then this rocket is going to blast off from Mars. It's going to have a sort of a beach ball or volleyball sized metal container with all these precious, priceless samples inside. And then we'll have a spacecraft that'll go grab these samples and bring them back to Earth and parachute them down into Utah.
So all the samples are all it's working now. So I know the Perseverance did have a bit of an issue there at the first one, because they drilled in and it just was like very porous and just went away.
That's my next slide.
Oh, okay. Sorry to get ahead of you, Scott.
Yeah, no worries. So this is a very, this is a joint activity between NASA and the European Space Agency. This is a very complicated aspect, complicated mission with lots of different moving parts. Goddard Space Flight Center, where I'm from, we're controlling the sample collection system. So there's this whole process of sort of isolating the sample and kind of breaking contact with Mars, because although we don't really think there's going to be any active biology in these samples, we need to, both protect Earth from these samples and also protect Mars from the Earth contamination, right? We don't want to open these samples and say, oh my, look, there's an amoeba on top of our sample. And it's like, well, that's because it was stuck in the sample container the whole time, right? There's sort of a funny story about the incredibly challenging purity and cleanliness that these sample tubes had to have before they went to Mars. So these sample tubes had to have less than one active microbe inside of them before they were loaded onto the rover. Well, you can only count microbes in units of one, right? You can't have a fractional microbe. So that meant that there had to be 0 surviving microbes inside the sample tube. This is unbelievably hard on the planet Earth. I was told, you can stick, you can stick something, a piece of metal, like say the size of your phone, into a blast furnace, hold it there until it reaches temperature, pull it out, immediately sample it. You will have active microbes on that surface because of microbes in the air falling onto the surface. So having something that's that level of clean, where there's no contamination possible, was really, really hard. It took a lot of challenging work to make those tubes so perfectly clean and free from contamination. So anyway, Perseverance is on Mars now, and it's doing this sampling. And so the first attempt, as Dan was alluding to, did not go as planned. So as you probably can imagine, we test these systems exhaustively on Earth. And so they tested the sample collection system on about every variety of Earth rock you can imagine being on Mars. And in every case, we got some sort of sample inside the tube. And the literal first attempt on Mars produced something that we had never seen before. It drilled in, we produced a rock sample sized hole on Mars, and we looked inside the tube and there was nothing there. And, they literally thought maybe it fell out onto the surface. They were going through all options basically. And what the best sort of answer seems to be is that this rock was just so sort of friable. It was so sort of low density that it just sort of powdered into non-existence and maybe made this small pile at the bottom. So it was really quite baffling. We thought we'd at least get some sort of debris inside the tube, but there was nothing there. So just try again. And the second attempt was successful. And so we got a perfectly nice rock core. We actually drilled 2 samples out of this same rock. So this is part of the sampling strategy, where what we probably will do, and I'm going to get to this a little bit later, but for a lot of these samples, we're going to create duplicates. And one we're going to kind of leave somewhere near, kind of where we are now, or probably a little bit farther along the road, in a sort of depot. And then one we're going to kind of take with us. And it sort of depends where Perseverance is in 5 to 8 years time, where we might send the sample return lander with this rocket and this fetch rover kind of to where Perseverance is going to be. Or if we've gotten Perseverance kind of stuck in a dicey spot, we might send it closer to this sort of depot, not too far from where we are now, and it'll collect those samples. So it's sort of in some ways like a contingency sample, right? So we're kind of taking 2 because we might be here, we might be there, and we want to make sure that we have this nice sort of collection in either case. So we took 2 samples in this rock, and I think a lot of the samples going forward will probably be duplicates. We have, obviously a finite number of these sample tubes, but the goal is to kind of get somewhere on the order of probably, 20 unique samples. And in some cases, we might bring duplicates back to Earth because those samples are particularly valuable. So what is a day in the life of a Mars rover? And so I have this sort of a wide smattering here of pictures. Both rovers have a laser, which is a spectrometer. Actually, it's called a laser-induced breakdown spectrometer. So it shoots this little laser beam out on a rock and vaporizes a little tiny bit of it. And the puff of gas and plasma that's created by this vaporization can be studied by the instrument, and we can tell what the rock is made of that way. So we do this all the time. This is sort of the rover's way to kind of get a broad sampling of the rocks nearby without having to reach out the arm and sample it directly. That little orange dot on the top is not Mars from a distance. It's actually an image of the sun. This is sort of more my bailiwick. We measure the atmospheric opacity, basically how much dust is in the atmosphere between us and the sun. And to do that, we take images of the sun. We basically point the camera right at the sun, take a picture, and we can measure how much of that light is attenuated by the dust in the atmosphere. And so we do that on a pretty regular basis with both rovers, every couple of days or so.
Is that how the sun would appear in the sky from Mars? Size?
Yeah.
I guess it's tough to tell without a.
Yeah, I don't think you can go with the size very well. Yeah. I mean, daytime on Mars would be perfectly bright. You wouldn't, unless you're like really in the middle of a dust storm or something. It's not like you would think the sky is dim, right? And it would still be too bright to look at. So we often will use the rover's arms, and there's several instruments on what we call the turret, basically the rover's hand. And we reach those out and place those on particular rocks to study the geology of the features of the rock. And then, of course, I have a picture of the rover's wheel, because a lot of times we drive. The rovers often will drive at least a few times a week, depending on what they're doing. There's different kind of phasing. Sometimes they drive almost every day. Other times they're kind of parked in one spot for several days because they're drilling a rock or sampling it or otherwise studying it for a long period of time. So, those are sort of the basic things we do. We drive, we use the rover's arm, and we take use of what we call the remote sensing instruments to study the rocks and the environment around us. And that's what the rover does on a normal day. For the Curiosity rover, because the rover's been there for now going on almost 9 years, over 9 years. We only operate the rover directly 3 to 4 days a week. Otherwise, the rover is sort of in pre-programmed activities. For Perseverance, because it's much newer, we operate the rover not quite every day, but most days. Something like 6 days a week. So how do we do that? How do we drive a remote control car that's 100 million miles away? And it's through virtual telecoms. We were doing this virtual telecom nonsense way before COVID to do this. We have people all over the world for both missions. Obviously, most are in the United States, but there's Canadians, there's Spanish teams, French teams, even some Russians on the Curiosity team. And we all sort of dial in using some collaborative tools and software. And we develop a plan for the rover's activities for a given day or several days. The teams themselves, the science and the engineering teams, are huge. They can be, several hundred people in total. But in most days, only, somewhere on the order of 30 are sort of actively involved in planning the rover's activities. It's a little more for Perseverance, it's a little less for Curiosity. And everything kind of funnels through the Jet Propulsion Laboratory in Pasadena, California. That's who directly operates and controls the rovers. And so everything kind of funnels to them. That's where the engineers sit, and they send the commands up to the rover.
Scott, when you're working on this, do you actually start going on to Mars time yourself? Do the people there, they go by soul so that you have these screwy hours eventually that you're working?
You're again anticipating my next slide.
Oh man, I've not seen your slideshow yet. So
I think it's 2 slides away, maybe.
All right.
So we communicate with the rovers through what's called the Deep Space Network. Some of you may be familiar with that. So it's 3 giant radio telescope complexes around the world. So always one of them is facing Mars. So there's one in California, one in Madrid. I actually took this picture. This is the one in Madrid, the big 70-meter dish, and then one in Canberra, Australia. And so we communicate through the DSN, through the Deep Space Network. We can communicate directly to the rover itself. So the rover has antennas to communicate with Earth directly. But actually, most of the time, we kind of use a relay system where we communicate through one of our orbiting spacecraft. And this is often just a much bigger data pipeline for us. So it's like going from, I want to say like let's just say a 3G network to LTE or to 5G or something like that, right? I mean, in both cases, it's still more like a modem, but we're communicating usually through one of the orbiting spacecraft and then kind of sending our data through them, and then they go back to Earth from there. And we can do the same thing with commands from Earth. But for whatever reason, if we need to, we talk to the rover directly all the time as well. We kind of usually just kind of send a test every day where we communicate with the rover directly, but for the most part, we communicate through the orbiters. There we go. And so, yeah, speaking of Mars time, so typically when COVID is not happening, we, for the first 90 sols, 90 days of each mission, we have Mars time, where everyone kind of goes to Pasadena, works directly to operate the rover and stay on the local time of the rover. And so Mars rotates at a pretty similar pace to Earth, but about 40 minutes longer per day. So it's about 24 hours and 36 minutes for Mars to rotate around. And so on Mars time, 8 a.m., the start of your workday is 40 minutes later every day. But we did not do that for Perseverance because of COVID. So we didn't all go to Pasadena, but the shifts were working on Mars time. I guess I should caveat that. We didn't all go to Pasadena, but the shifts were still on Mars time. Now, we've been on the ground for Perseverance for quite a bit longer. And so that is now off, and we're back to just sort of regular Pacific time for planning Perseverance. And we've been doing that for Curiosity, obviously, for many years now. So kind of getting to the end here. So where are we going from here with our 2 rovers? So on the left here is Perseverance, and the white dot where I'm highlighting with my cursor, that was our landing spot. And when we landed there, we kind of thought there was two options to get to the beautiful river delta here that we're targeting, and what really brought us to Jezreel in the first place. So the first is sort of the northern left turn, or the southern left turn is the second option. And after some discussion, it was decided to do the southern route. And so this blue star is about more or less where the rover is sitting today. So we're not too far from the landing site still. And the ultimate plan is to sort of is to drive around some of this more dangerous sandy terrain, rocky terrain, to get around it and then go back up through this sort of channel here up to the delta and then climb on top of it. And of course, sampling along the entire way. And then, as I mentioned before, eventually kind of driving up parallel to or through the valley and out of the crater entirely. And there's even sort of a long-term plan to maybe go to an interesting region it's quite a distance. It's like 30 to 40 kilometers away. So it'd be quite a long time before we get there. Curiosity, you can see its trail here in the white, kind of going through some of these geologic units of Gale Crater as we climb higher and higher up Mount Sharp, the center mountain of Gale Crater. And you can see here we kind of have a pretty wandering path usually, and then it got much more sort of straight and defined in the last couple of years. And what we're doing is now we're kind of climbing onto what we call this green hue pediment. We're quite close to it now. And we're going to climb onto this and then kind of go up this ridge line, which also appears to be perhaps an ancient fluvial feature, into these more sulfate-rich rocks. So again, what Curiosity is doing in particular, that's a little different from Perseverance and Jezreel, is we're kind of going back through Martian history here a bit as we climb higher and higher, where lower down in this clay-rich area, we think that water persisted for longer periods of time and in different ways. And we're kind of climbing through the history of Mars drying out as we climb higher and higher up this sulfate-rich unit and eventually even beyond it. And so that's where Curiosity will be going over the next few years. So with that, I'll conclude, and I'm happy to take whatever questions there are.
Wow, it's great stuff, man. Thank you, Scott.
Thank you.
Yeah, there's a couple of questions, and let's keep them coming in here too. So Stephen Schreier had asked too, the color in the photos that you've been showing to us tonight, are those actual color things? If you were standing on Mars, is that what you would see?
Yeah, good question. So a lot of these images are pretty much natural color. Like this one in particular here is pretty close probably to true color. Sometimes you'll see images, and you guys are probably better at, I'm trying to look at some other ones here. You guys are probably better at image processing than I, but a lot of times you'll see images that are white balanced. And so the sky will look a little bluer and the colors will all seem kind of a little bit brighter and kind of pop a little more. And that's not really what, you should keep an eye out for that, because that's often images you'll see. I mean, famously, some of the first Viking images that were sent back had this like beautiful blue sky. And everyone was like, oh, wow, Mars has blue sky. And it was like, no, they just white balanced the image and made the sky blue, and it made the colors on the rocks pop a little more. So the colors would, to your eye be generally quite muted. Like here, the sky looks a little bit, maybe bluer than I think it naturally would be. So I think this sort of color is a little bit more closer to what your eye would see. A lot of brown, a lot of yellow, a lot of reddish orange.
Oh, it's amazing. Lynn had asked earlier too, you showed clouds of water earlier. She's wondering, where does the water come from? Yeah, this shot here. Where does the water come from?
Yeah, so Mars has water. The North Polar Cap of Mars is predominantly water ice. So seasonally it gets covered with carbon dioxide ice, but the polar cap itself is a big old chunk of ice, of water ice. There's also water vapor in the atmosphere, and there's water ice underneath the surface in a lot of places. So I mentioned those fresh impact craters that we see. Well, actually, where we see those the most are at the high latitudes, where these impact craters come in and they smash into this ice-rich layer. And so the crater just pops out all these chunky bright ice particles. And so they're very visible to satellite images. Whereas if you just kind of hit, created a new crater on, some of this terrain, it's not going to be very noticeable because it's all just going to look the same for the most part. But we've had these impact craters hit in these ice-rich regions of Mars. And so you see that the ice is buried very near the surface. There was another lander mission called Phoenix, which was operated back about 15 years ago now. And it landed at very high northern latitude, sort of like, the Greenland type latitude of Mars. And it dug down just a few, centimeters below the surface, and there was ice under the surface there. So Mars has a fair bit of water. I mean, if you melted all the water on Mars and kind of put it all onto the surface, it would cover the whole planet in about 30 meters of water. I mean, it's more than you'd think. That's still way less than Earth, but it's far from nothing.
I think there was plans some time ago. I don't think it ever happened, but somebody was going to land up in the northern pole and actually just land right on the pole. And I don't think it happened, but is there plans to do that again?
So I think you mentioned the Mars Polar Lander, which
that's it, Mars Polar Lander.
Yeah, which was supposed to land, I think, in 1998. And it definitely reached the surface, but
that's right. It just went faster than it should have.
Yeah, we call that litho braking instead of aero braking.
Right.
So it litho braked into the surface, and we never heard from it again. But there are certainly discussions about landing directly on the ice. That's something that a lot of people, including myself, would be very interested in doing. But there are no sort of active missions planned to do that.
Good question from Mike Lyons here. How high is the edge of the delta inside the crater? It looks like a pretty sharp edge from the satellite photos. What say you?
Yeah, that's a really good question. I don't have the exact answer, but it is tens of meters high. So yeah, it's there are places you can see it's a little bit more gradual. I think like this area here, I think is sort of the notional ascent route right here, where you see it's kind of like it looks a little bit more sloping and sharp versus this sort of very cliff-like edge here, which like I said, I think is a few tens of meters high.
Stephen Schreier asked another question here. Does Perseverance have a camera that can take a microscopic image just in case you stumble along, and you see, hey, there's some like fossilized organics? Would we be able to see that with Perseverance?
Yeah, so both rovers have a what's called a microscopic imager on the rover arm. But they are the smallest they can get. The smallest sort of pixel size they can get is, I think, about 50 microns, which is enough to see, tiny little sand grains and tiny little variations in the rock. But that's still way bigger than a fossil or a microbe might be. If there's like a trilobite, in one of those rocks, yeah, we're gonna see it. But if it's something, like a amoeba scale, something like that, it's just too big, or the image resolution is too big. We can't see that.
And he had another follow-up question too. Hypothetically, how long could Perseverance survive after the primary mission is done? Will it continue to operate like these others seem to have just, they're the Energizer bunnies? Are they going to keep going?
Yeah, so that's the good thing and bad thing about nuclear power is that it could keep both rovers going for a long time. So Curiosity, for example, we have, or let me step back a little bit. Both rovers are powered by plutonium. Right, that's our radioactive power source, is plutonium. And the plutonium generates heat. The heat generates electricity. The electricity charges our batteries. We actually run off of the batteries, not directly off the isotope. So it's imagining like, you're trying to do things on your phone, but you always have your phone plugged in because you're running your phone off your battery, but you're trickle charging it with the wall, right? That's right. sort of how it works. And so the plutonium radioactively decays all the time. So for example, Curiosity, we are producing only a little more than half the power we did when we landed 9 years ago. We just gotten a lot better at using the rover, so we kind of don't need all that power anymore. But we're getting pretty close to the point, probably in another 18 months to 2 years, where we'll have to have recharge days, where some days we just don't do anything. We just charge the battery because we don't have enough power. Perseverance is obviously a long way from that, right? It's probably at least 10 years away from needing that sort of recharge zone. But yes, then there will come a time where probably the rover doesn't drive anymore. And then there will come a time where we just can't keep it operating. And that's a long time from now. NASA funding might be the harder limit than the power source. But there will be a day where the radioisotope power just is not enough to charge the battery and the rover will die. Still a long way off, though.
Yeah, that's good. Franco, who actually searched and found you and invited you to come speak to us tonight, which I really appreciate, has a question. Franco, what was your question?
The question is, how far are the rovers from each other at this point?
Yeah, I don't actually here. I do. Let's see if I can go to, which slide is it? This one.
Yeah, that animation. Yeah, that one.
Yeah. So here is, so Curiosity and Opportunity we're really on about exact opposite sides of the planet.
Oh, really?
But Perseverance is a little bit closer to us, to Curiosity. So I'm going to try. It's right about here. You can see my cursor.
Mm-hmm.
So it's about 90 degrees of longitude away. And Perseverance, or sorry, Curiosity is about 4.5 degrees south, and Perseverance is like 14 or 17 degrees north. So we're obviously in different hemispheres as well. And Perseverance is a little farther from the equator, but we're kind of, this dark region here is Syrtis Major. You guys are astronomers. You probably have seen Syrtis Major through your telescopes. And Isidis Basin, where is this brighter feature here, and Jezreel Crater is right in the boundary between Syrtis and Isidis Basin, and so that's where Perseverance is.
Thank you.
Mm-hmm.
Steve Labkoff, you had a question?
Yeah, I was curious. The rover that has plutonium power, does it also have solar panels that collect additional energy, or is it just completely nuclear powered 100%? So you don't have to worry about cleaning panels and things.
Correct, just nuclear powered. So yeah, all of our spacecraft, Mars or not, have been either nuclear powered or solar powered. There's never been one, to my knowledge, that has had both. So right now on Mars, we have the nuclear powered rovers, Perseverance and Curiosity, and the InSight lander, which is actually is quite close to Curiosity. It's like right about here, is solar powered, and the solar power panels are actually getting quite dust coated for InSight.
Have they ever thought
now for 3 years? What?
Have they ever built, like, don't laugh, but like windshield wipers for the panels or something like that?
Yeah, there's
to clean them.
Yeah, there's been a lot of looking into that, and it's been decided is that it's a lot easier just to make a little bit bigger solar panels, and so that it'll generate enough power long enough to complete your mission, versus coming up with a way to bring something to clean off the panels. It's a lot lower risk. It's a lot simpler just to make your panels a little bit bigger, because we know how dusty now. We've sent enough spacecraft to Mars. We know how much dust is going to get covered on them over time. And actually, for Spirit and Opportunity, it was actually quite surprising that they got cleaned off and then they survived as long as they did. Those rovers, their mission was only 90 days originally, and it was expected they would get to be, if you listen to some of the mission people at the time, they expected to get 6 months, and they thought maybe they'd get a year. But by a year, the panels would get too dust coated and the rovers would die. Well, they survived. Opportunity survived for 15 years, and that's because of those. And that's because of these dust devils blowing around the surface and cleaning off the solar panels. And we really didn't know that would happen until we sent the rovers there, and they just kept getting clean. And they kind of reached this sort of steady state where dust would fall on the rovers, they'd get cleaned off, dust would fall on them, they get cleaned off, and you sort of kind of bounce around this middle zone where it was enough to operate, less than what it was when it was freshly landed on the surface, but enough to operate. And so we were hoping for InSight the same thing would happen. And for whatever reason, wherever it is in Elysium Planitia, it is not getting those cleaning events. And so it likely will fail. The mission will die next year sometime. But again, that mission was only supposed to be 1 or 2 years, and it's now survived for over 3 or nearly 3. So, it's well past its primary mission phase.
Scott, we have a question from YouTube. Pete L had asked, what is the scale of the picture of the Delta area, and how far between the landing sites and the exit of Lazaro? And, what is also, just to throw into that, how fast can Perseverance drive? How fast can it go?
Yeah, good question. So this landing site here has about a radius of about 10 kilometers. So, there's your sense of scale there. Is it radius or diameter? Oh, here's the scale bar. Perfectly. Yes, 10 kilometers. So there's your sense of scale. So it's not that big. Again, that's much smaller than the landing ellipses we've had before. So how far does it drive? How fast it drives? Perseverance has a little bit more advanced, self-driving capabilities than Curiosity. It's sort of like, you got your Tesla upgraded, I guess. Perseverance, when it's sort of when the keys are fully given away and it's all set to go, and it needs to drive this far, it can drive about 200 meters in a day, up to 200 meters in a day. Curiosity doesn't go quite as far. The longest drive it's ever done, I think it did 140 or 150 meters, but more often we only do 10 to 40 meters in a given day. And the driving time, it does that. It doesn't take a whole day. It does that driving in a couple hours usually. 1 to 2 hours is sort of the driving time that it's allocated for to get that distance. For Curiosity, we sort of program the drive a lot more directly, like drive 2 feet or drive 1 meter, turn left 30 degrees, drive 10 meters, turn right 60 degrees, and so forth. For Perseverance, we just kind of give it an endpoint, and then it navigates itself, and it's taking images and sort of developing a terrain map and avoiding bad stuff and driving on good terrain to get to where it wants to go. So Perseverance is a little more self-driving.
HK has a question, and this is a big if, but say the rover's happily driving around, minding its own business, and smashes into an ET. So what if it does actually meet intelligent life? What communication choices would we have from us to them? I mean, could we wave the flaps around a little bit and wink an eyeball, or hand signals? What would we do if we did see something like that on Mars?
I can't even say.
Yeah, I know it's a tough question.
I think it's so far out of our expectation, but we do have those the laser induced breakdown spectrometers on both rovers. We can create little holes on rocks, so we could probably carve something into the rock. We could carve. We could make a circle and show them that we know what pi is, and and of course, you would hope that if they realize we've managed to send a remote control vehicle, a couple 100 million miles, that we do know some basic mathematics and some basic science. But here's the thing I actually tell people, which is maybe a little more likely to happen. About let's say we saw a puddle, right? Liquid water right there on the surface, or a damp spot, or something like that. That's more plausible, not likely, but more plausible. But we'd have to, get away. Frankly, we'd have to get away from it, because the rover, particularly Curiosity, less so Perseverance, but it was not designed to be in a place where active life could be present. Right? It was not cleaned sufficiently that we would, if we saw something like that where we think life could be active today, like in a liquid water puddle, we would risk contaminating it with Earth life that's still on the rover in some way. And so we would have to get away as fast as possible, particularly with Curiosity again, but Perseverance probably too. We would turn around and hightail it out of there because we don't want to risk contaminating that little oasis with whatever creatures are still crawling around inside our rover.
Well, let's just kind of wrap with a couple more questions here. There's a few more here. Steve Schreier has another good one. Could a spacecraft being designed collect the Perseverance rock samples and then bring along like a replacement plutonium power supply or a battery for Perseverance? And obviously that might be a little complex to do, but he also wanted to thank you and say it was an excellent presentation.
No, thanks. Appreciate that. So that's an interesting idea. I've actually never heard that suggested before.
I hadn't either. That's a good one. That's different.
So I'll say that there's probably no real reason it couldn't carry more plutonium fuel rods with it. The trick is sort of hot fueling a Mars rover on the surface of Mars. Hot refueling, right? So there's no way to access the kind of to get into the power source, what we call the radioisotope thermoelectric generator, the RTG. There's no way to really get into it now, right? It's all been kind of closed up and sealed up and everything like that. So there's no access port where you can kind of slide in a fresh battery or a fresh tube of plutonium to get it charging. So you'd have to come up with some, no doubt, very complicated procedure to do that, and then bring those materials and tools along with the next mission. So to put a long story short, NASA considers those types of things, too complicated and not worth the effort ultimately. And that
what's wrong? What's so bad about leaving radioactive waste all over the surface of Mars? What could go wrong?
There you go. Exactly.
One last question from Morris, and I do love talking about Ingenuity too, and Morris had asked here too. How does the helicopter move forward and backwards and turn when its rotators are top of each other? They're turning in different directions. So I think he's more worried or more interested in the mechanics of this. Maybe a little outside of your shtick, but
that's a great question. I don't have a great answer. I think it has a little something to do with like the tilting action of the blades, and maybe sort of I think that's mostly it. I think it's a little bit of the tilting action, but honestly, I don't have a good answer. There's probably that information online somewhere, but I can't tell you for sure.
Well, Lapkov had a little note there too. Go ahead, Steve. Just say that.
Just out of curiosity, with NASA launching small power nuclear devices in effect, what would have happened if there was an accident and the payload exploded in the sky? Would that have created any kind of? Is it just too little? Is the amount of nuclear fuel just so small it's irrelevant, or would it have caused a problem?
Yeah,
we've been doing this for like 50 years, though, haven't we? Yes.
So great question. I mean, this is there was actually a lot of protests in Florida back in 1997 for the Cassini spacecraft launch, because Cassini had a nuclear power source, went to Saturn, and it had a lot more plutonium than either of the Mars rovers, because it was so far out and had such a big spacecraft, and it needed a lot more plutonium. So it actually had some protests for people kind of protesting that very thing. If the rocket exploded on the pad or exploded in flight, and it showered the Atlantic Ocean or the east coast of Florida in plutonium, and so NASA goes through a really exhaustive safety regimen with various federal agencies to make sure that would not happen ultimately. So there's any number of different ways that they test this and they validate this, that even in most likely scenarios or the most unlikely scenarios where the rocket explodes in flight or explodes in the pad, that the fallout or the risk to the environment for the public would be very, very minimal. So there's a big process for these nuclear powered spacecraft that they have to go through for that very reason.
Thank you.
I think every animal on Earth now has a little cesium in them anyway. So what's a little bit more?
Yeah, that Teflon.
Right, that and Teflon. Yeah, we got everything. Scott
So
Guzewich, I'm sorry. Go ahead.
Oh no, I was going to say one more thing about that is like, the plutonium does have a pretty short half-life though. That's sort of it though. So even if the radiation, or the plutonium somehow got out, it doesn't stay radioactive for too long because it does have a pretty short half-life. So
It only has to kill you once. Once will do. Scott Guzewich, it's a pleasure. Thank you so much for the talk tonight. That was really interesting, and man, I just go on this stuff all night. So thank you for that.